Here is details to a solution for one of the force tables from class time, and they're a little complicated. I have to do some things just so to limit the amount of calculations you need to do. You need to be very careful about the angle reading. So this was one of the tables. It looks like that was 76 grams of mass hanging on that string there at 0 degrees. Here was the mystery mass hanging there. That's the question mark. You can't see it. It's been obscured in this diagram. And then down here was 98 grams along the string here. That was the other tension. So this is tension 1, and this is tension 2, and this is the tension on the mystery mass. Best thing to do is put the mystery mass tension on one of the axes. So I have it, I call this the y-axis, which forces you to make everything relative to that now. So this is at 56 degrees, which means the y-axis would go down to 236 degrees on the force table. And the x-axis then would be 90 degrees rotation. So 56 plus 90 is 146. So that's where the minus x-axis is, and the plus x-axis is at 336 degrees right there. So my coordinate axes are in blue. So I've redrawn the important information here on the side, and when I do so, I've picked out two angles, this 56 degree angle and this 39 degree angle between the y-axis and tension 1 and tension 2. My plan is to work with the y components of these two tension forces, because those combined with the tension on the mystery mass must sum up to 0, because all the forces must sum to 0 on the x and y axes, because our object is at rest. This is equilibrium. Calculate tension T1. I take the mass that's hanging in kilograms, very important to convert the grams to kilograms, multiply it by G on Earth, 9.8 newtons per kilogram. So that's my tension force T1, and T2 is that amount of mass hanging times G, and so that's the tension force on T2. So I have another diagram here, and I label tension 1 with its value, tension 2 with its value that I just calculated, and those are the hypotenuse of two triangles you should see there. And what I'm looking for are the y components of those tension forces, which I am highlighting right there. So using the trigonometry, the angles that we've already established, and the hypotenuse of these triangles, which are the tension forces we just calculated, those are the two things we need to calculate those two unknown sides. First, looking at this triangle right there, using trigonometry and a cosine relationship with 39 degrees, cosine of 39 degrees times the hypotenuse will give me the y component of that tension force, and it's 0.746 newtons. And the other triangle is this one, and see there that that's 56 degrees. So, and the cosine will give me the y component. Cosine of 56 degrees times the hypotenuse there is 0.74 newtons. So T2y equals 0.412 newtons. So I now have those y components. And the last step is to do a net force equation, and I'm working with the y-axis, and I know all those forces are in equilibrium. They should sum to 0. On the y-axis, I have the mystery tension. I have the y component of tension 1 and the y component of tension 2. So those all add up to be the sum of the forces on the y-axis, and I'm going to actually solve For Tm here, rearrange these symbols to solve for Tm. Tm must equal the sum of all the forces minus y component, the y component of T1 minus y component of T2. I know that the sum of the forces is 0 because it's an equilibrium. And I'm subtracting, this is important here, subtracting a minus 0.746 newtons. Why minus? Well, I decided to call this direction plus and this direction minus, and tension 1's y component is in the negative direction. So I need to indicate that direction with that minus sign right there. And that's important. And then subtracting the y component of y2, that's on the plus side up there. So that's just subtracting a positive. And the result of this summation, which is really subtraction, is this right there. 334 newtons. And having that, I can make use of this relationship that we know. The weight is the mass times gravitational field strength. I can solve for the mass in this case, and remember that tension force is equal to the weight of the hanging mass, so the weight of that hanging mass is the tension force. That's the 0.334 newtons divided by g, which is 9.8, and I get the mass in kilograms, 0.034 kilograms, and what I saw in class was there was actually 33 grams hanging there, so this is off just by a gram. And this is the solution for this force table.